Hi ladies and gentlemen, welcome to lesson 16. We're going to take a look at what is arguably Professor Strang's greatest contribution to linear algebra education. It's the concept of the four fundamental subspaces and how we take a look at any linear transformation, in other words, any matrix, and kind of break it apart into these constituent pieces, which are the fundamental subspaces associated with things like null space and column space and row space. There's a fourth one which we'll introduce today. Let's take a look then. We're here in section 3.5, and the conversation for today is largely about the existence of these subspaces along with their dimension. We'll go through a couple of examples to look at dimension. We'll talk some about basis, but that's really the deeper conversation that we're going to have in the next lesson, where we take a deep dive into what these fundamental subspaces are and how for any A matrix we can build them. So first things first, we're going to integrate with this conversations about rank and dimension. We'll also have the basis conversation a little bit, but that's really, like I said, for next time. So what we're talking about, and let's go back for a second. Remember, we discussed the fact that there is a function defined as matrix multiplication for any matrix A. And now I'm thinking about A is rectangular, m by n. It could be square, but I want to be more general than that. I want to think about it being rectangular. And what we're doing then is we're thinking about the important pieces of this matrix. We know that the matrix A maps from, in general, it's going to map from Rn to Rm. The input vectors, the x vectors that we're multiplying in, have to have n components in order to be multiplied into our A matrix. And then the outputs are going to have the same dimension as the number of rows. So we'll have vectors in Rm. So we can kind of tell from that, and what we already understand about matrices, that A is mapping, as we've discussed before, and now instead of the clouds that I was drawing for you, we have this kind of more systematic picture. Please don't be confused. We're not talking about just two-dimensional vectors. The fact that the picture is drawn the way it is will become more evident when we get to chapter 4. Right now, we're just thinking about these two sides, Rn side and the Rm side, as the input and output sides. And we want to look at the spaces, kind of the decomposition of those sides. So we know that given any vector over here, x, that when we multiply by A, we get an AX vector over here. So we're not so interested in individual items. We're interested in what that means for the system. That means that we have a fundamental subspace, which is the column space of A. This is the set of vectors in Rm, which we can map to as a linear combination of the columns. And we've talked about this. We also want to talk about the null space. I've color-coded the squares here. Strang doesn't do this, but I've done this to demonstrate the red is associated with the A transformation. Because for every linear transformation, there is a transformation that goes in the opposite direction if we consider A transpose. And we'll talk about that. But this A transpose is what fills out the picture for us with respect to the four fundamental subspaces. So the column space, which is really the range of this linear operator over here, the column space is one important aspect of A. What is the other one? Well, we just talked about that a little bit ago, and that's the null space. The null space is on the input side. The null space is the vector space in Rn, where everything from this space maps over to the zero vector, which is this purple intersection point, if you will. So this is the null space, this is the column space. That idea matches exactly with the transpose. When we take a matrix and we think about the transpose of it, we are literally coming up with LA transpose, which is going to map, and I'll refer to them as y's just to have it a little bit different, and we'll see why this is true in a minute. But this is really A transpose times y. So we have y inputs on the Rm side that are now being mapped over to Rn. The spaces match up exactly the same. The column space of A transpose is over here, and the null space of A transpose is on the input side. You recognize the column space of A transpose, that's the row space of A. So the row space of A, the column space of A transpose, those two things are the same. And we want to take a look at the dimensionality. That's a big part of today's conversation associated with these different spaces. I think it's easiest if we look at an example. So let me put in a fresh picture here, just a second. All right, so I have a fresh image here, and I have an A matrix that we're going to consider. So let me copy that down on the... All right, so here's our A matrix, which I have in here. And what we want to do is we want to think about these different spaces and what their dimensions are. Remember, the definition of dimension is the number of vectors in every basis. And so we're thinking about this, and we're going to think about the rank of this matrix as well. So looking at this A matrix, we can tell immediately that it is rank 1. We can see that all the columns are scalar multiples of each other, and of course the rows are scalar multiples of each other, so we have a rank only of 1. What I want to do then is talk about what the column space is. For this particular matrix, we can see that the column space of A is just the span of the one column that we have. So it's the span of the column 2, -1. That's the column space. And we also see where we really want to start is with understanding the mapping. The mapping is taking vectors of dimension 3 that are being multiplied against A and mapping them to vectors of dimension 2. So we have R3 is mapping over to R2. And we can just tell that by the dimensions we have here. So here we have the column space, which is the span of this thing here. The dimension then is dimension 1. Let me write down the RREF, and I'm going to write this down as R0 using Strang's notation. So this would be 1, -3, 2, 0, 0, 0. So we can tell what the rank is. The rank is the dimensionality of the column space. The column space has dimension 1 because A has rank 1. Well, what's the row space? The row space is the column space of A transpose. And at least for this first example, we want to be very clear about this. So let's write down what A transpose is. That's just 2, -6, 4, and then -1, 3, 2. So we can easily see that the column space of A transpose, which is the row space, is the span of the vector 2, -6, 4, or remember, when we do the RREF, we can also pull the basis vectors out of here. So it's the span of 1, -3, 2. The dimension of the column space of A transpose is also 1. Both of the column spaces, the column space of A and the column space of A transpose, they are always going to have the dimension of the rank. So that's a really important point, and he makes that point throughout this discussion. Well, what does that leave then for the null space of A transpose and the null space of A? Well, we know what the null space of A is. The null space of A is any vector that we can multiply times A or times R naught and end up mapping to 0. So the way we find this is using Strang's special vectors. Think about, right? So the null space is always the same. The null space of A or A transpose, we'll deal with A first. The null space of A comes from solving ax equals 0. But ax equals 0 comes, the solution comes from doing RREF of a, and then we identify the free variables. So in this case, we have free variables in the second and third locations. So while we are not going to necessarily discuss today what the null space of A is with respect to the basis vectors, we can definitely see that the dimension of the null space is equal to 2 because we have two free variables. Same thing as we've been talking about with respect to solving. In this case, we're solving the homogeneous equation. Similar conversation then, if we look at the RREF of A transpose, the RREF of A transpose will have one non-zero row and it will have one free variable. So on this side, we have the dimension of the null space of A transpose is equal to 1. So we're not talking about what the actual basis vectors are. We just want to understand at this point the size of these different subspaces. And remember, the dimension here is the rank. The dimension here is the rank. And then what we find is that we have to fill up the entire space. In other words, we need the dimension of the column space of A and the null space of A transpose to sum up to 2, because we have to cover all of R2 between these two things. So if the dimension of the column space is 1, that leaves us 1 left over, and that goes in the dimension of the null space of A transpose. Similarly, rank is 1. We know the dimension of the column space of A transpose, the dimension of the row space is 1, but on this side, on the input side, we have R3. So we have 2 dimensions left that we need to cover, and both of those have to be in the null space of A. So the dimension, when we sum up the dimensions on the input and output sides, need to be equal to the size of the vector space that we are mapping from and mapping to. This is a big takeaway for Strang here, and it's really covered in here. He talks about the dimensions of the column space and the row space, and then the dimensions of the two null spaces. You'll notice that he calls the null space of A transpose the left null space. Let me explain why he uses that terminology. So you know that when we are solving for the null space of A, we are solving AX equals 0. Well, if we want to solve for the null space of A transpose, what we're going to end up doing, and let me not use that notation, it might confuse you, we're going to end up solving A transpose times a vector equals 0. And that's really the y vector equals to 0. The reason it's called left null space is what I'm going to do is take the transpose of both sides of this equation, which I can certainly do. So when I take the transpose of A transpose y and set it equal to the 0 vector transpose, that is going to give me the y vector transpose times A is equal to the 0 vector transpose. Now, most people, when they write the 0 vector, are not going to put the transpose on it. So that is there simply to designate that it's a row vector, but as I said, that rarely happens. Let's go back then and look at our specific example. We have y vector transpose, which is being multiplied by 2, negative 6, 4, negative 1, 3, 2, and we're trying to get out of this the 0 vector. So this is why it's called left null space. I'm looking for the left multiplication solutions that are the null space for A, which turns out to be ultimately the null space of A transpose. So this multiplication on the left is why it's called left null space. And we can pretty much see what this is going to be. We can see that if we pick a y vector as any scalar multiple of 1, 2, then when we sweep that through, so that y vector is going to sweep through and it's going to get 0, 0, 0. This just, as an example, tells us how we could get the null space of A transpose. The null space of A transpose is the span of the vector 1, 2. And that is something that we notice about this. Looking at this, you have to be a little bit observant here. This vector is orthogonal to the column space of the matrix A. It's orthogonal because I'm really taking the dot product of y with each column of A, and what I'm looking for is the 0 for each of those, which means it would be perpendicular. I'm looking for the vector that is perpendicular to the column space. We'll talk more about this later. So this is why it's called left null space. Here's an example, and we're just going to walk through this example just as a repeat. He explains all of the information down here. I just want you to recognize that from the RREF, we have the answers to these dimension questions immediately. So let's think about the dimension of the column space of A. And what we're thinking about right now is we're thinking about this R0 is the RREF of whatever our original A matrix was. We don't know what it is. That's fine. We'll talk about basis later. What we want to do right now is understand the dimensions. So the dimension of the column space is the number of linearly independent columns. And we can see that we have 2 pivot columns. And so those 2 pivot columns mean that this dimension is 2. That dimension, as you're well aware, is also the rank. So the rank of A is equal to 2. Well, but we know also that the column space has a dimension equal to the rank. So the dimension of the column space of A transpose, which is the row space, is also equal to 2, as we've been discussing. The way I can see that from the RREF is because we have 2 non-zero rows. So this highlights a really important point. We will always have the same number of non-zero rows as we have pivot columns because they both represent rank. So let's go and take a look at the null space then. So what is, let me change colors, what is the dimension of the null space of A? Well, I'm answering this question by considering solutions to AX equals 0. That's what I'm after. Right? And those solutions we know come from Strang's special solutions. They come from looking at the number of free variables. So let me shift colors. I can see that I have 1, 2, 3 free variables when it comes to solving the homogeneous equation. So this is the RREF of A. I can think of it, even though it's not augmented, I can think of it as being augmented with the 0 vector. I just didn't include the 0 vector. So 3 would mean that the dimensionality here is equal to 3. Finally then, the last question is, what is the dimension of the left null space? The null space of A transpose. Well, the null space of A transpose is the piece of information that is not immediately available right here. It really is, but let me show you how we're going to count this. And this goes back to what Strang talked about at the beginning of this section. It has to do with the number of 0 rows that I have. Right? It has to do with the number of 0 rows. And the question is, why? Remember, the red was associated with the A matrix. Right? So we are always mapping Rn to Rm, even when I was showing you the cloud pictures. We're always mapping Rn to Rm. And we know that A is associated with this, right, and the null space. And that means that I have dimension because, And it's only because the dimension of the column space and the row space are the same. These two things are always equal to each other. It's because those two are always equal that I know that I'm mapping from R5, I get that, onto, well, what's left? What's left is the dimension of the column space of A transpose and the null space of A transpose, but again, these dimensions are the same. They're both equal to the rank. And what we have is we are mapping onto R3. So we could tell all of that immediately simply by looking at the size of the matrix here. But this is just confirmation that we're getting the same information when we look at the dimensions of the four fundamental subspaces. It's all tied into the dimensions of the matrix that we're talking about, along with its rank. If you know the dimensions of the matrix and you know the rank of the matrix, then you can answer the question about all four dimensions of these subspaces. And he talks about that. So we're leaving you to read through all of this material here. He walks through this specific example. He does look at some of the basis information. For example, he talks about his special solutions here for the basis of the null space. Read through all of this material all the way down. He emphasizes the left null space and solving the left null space question. Looking at coming up with a basis. You don't need to worry so much about the basis information for the left null space here. We'll talk about that next lesson. And then he finally gets to the picture that we've been talking about all day. This is his big picture, his contribution, if you will, to linear algebra education. This whole concept that we've been talking about. Row space, which is the column space of A transpose, null space, column space of A, and the left null space. And then he talks about the dimensions. These are both dimension R for rank R for the matrix A. And then this is n minus R because we're mapping Rn to Rm. And then the dimension of this null space is m minus R. And I have one more example that we're going to walk through. We'll fill this one out. Again, not the basis, just the dimensions. So let's remind ourselves. This is the column space of A. This is the null space of A. And then with the null space, on the mapping side is the row space, which is the column space of A transpose. And then on the output side is the null space of A transpose. And we just want to know what these dimensions are. So here's our matrix A, and I can make it look more like a matrix. I just took these straight out of MATLAB. And so the matrix is 5 by 4. So let's do dimensions first. Always we want to start with the dimensions. We are mapping vectors from R5 into R4. R5 into R4. So we're mapping R5 into R4. What that means is that the dimensions of these two spaces has to sum to 5. And the dimensions of these two spaces has to sum to 4. Start at the top with the column spaces. That's just equal to the rank. And we can tell immediately what the rank is. We have 1, 2, 3 pivot columns. And so the rank is 3. So the dimension here is 3. And of course the dimension here is 3. And now it's just a matter of difference. So we know the dimension down here is 2 because we have to sum to 5. And we know the dimension down here is equal to 1 because we have to sum to 4. We can also get that information from the RREF. We can see that we have 2 free variables. So we have the 3 pivot columns and we have 2 non-pivot columns. And so because we have 2 free variables, the dimension of the null space is 2, and that's what we found. And then as I told you before, we have a 0 row here. Each 0 row is what is contributing to the dimension of the null space of A transpose. That's how we can fill this out, and we'll talk more about the bases next time. So he talks about the 4 fundamental subspaces. Again, more material for you to read. The stuff that he talks about in this section is really begging for us to write some true, false, and multiple choice types of questions. All of the information that's in here. Then he gets to what he considers to be the fundamental theorem of algebra, specifically the fundamental theorem of linear algebra. So let me highlight this. This is the fundamental theorem of linear algebra, part 1, which he says has to do with the dimensions of these spaces. So no disrespect to Professor Strang, but I don't think that is the fundamental theorem for linear algebra. Here's what I think the fundamental theorem for linear algebra is. And it's very much in line with what we talked about a couple of lessons ago. So I think the fundamental theorem of linear algebra is the following. Every linear transformation between finite vector spaces. We're not really doing infinite dimension vector spaces in here. We are talking about some of the function spaces, but we're talking about them with finite bases. Every linear transformation can be represented by a matrix. And every matrix that we see is representing a linear transformation. Remember we talked about President Trump being huge? This is the huge result for linear algebra. Every linear transformation we can represent as a matrix, and every matrix we see represents a linear transformation. This is the critically important piece of why we talked about this. Every matrix A is associated with a linear function, a linear transformation. These two things are always connected. So if we have a linear transformation, we know we can come up with a matrix representation for it. It just depends on the basis that we select. And if we have a matrix, we know that that represents a linear transformation. That is the bottom line for linear algebra. And it's the reason that it's so powerful is because that statement is always true for all vector spaces as long as they're finite dimension. A little bit more of a conversation in here about the dimensions, another example. And then we have this example here, which is talking about an index matrix. So let me highlight this for a second. So he's talking about an index matrix for a graph. And he provides that matrix here. You don't need to worry so much about the applications. Just take a look at this matrix that he provides. Of course, he has left out all the zeros, which is his prerogative, but the reality is that makes it a little bit confusing. But what he walks through then is, through here he talks about, okay, here we have a matrix A, and that matrix A is mapping R4 to R5. And what we're interested in are the column space, the null space, the row space, and the left null space. For every linear transformation, we have these things, and we're interested in what they are, what they're doing. One more item, so he talks a little bit more about the application here as it is, applies to Kirchhoff's current law and Kirchhoff's voltage law. These are some things that you remember from physics. So he talks about the incidence matrix with respect to that specific application. We won't be doing this specific application, but it's a good thing for you to be able to look through and understand where one simple application comes from as it relates to linear algebra. One more item here, which is a review of something that we've been talking about, and we've addressed this already, but he does it in a little bit different way here. He's looking at, again, the fact that we have a decomposition for the matrix A, which is equal to C times R. The specific example he provides is a 3x2 C and a 2x3. Let me erase that bottom part there. A 2x3 R matrix. We have our C and we have our R. But now thinking about the 4 fundamental subspaces, what's the dimension of the column space? Well, that's going to be the number of columns that are in this matrix. What's the dimension of the row space? That's also the number of columns that are in this, right? That's the rank. The rank is the number of linearly independent columns. It's also the number of linearly independent rows. And then he goes on to say, as long as we know the dimensions, then we can calculate the dimensions of the matrix A, is what I mean. As long as we know the dimensions of the matrix A, we can calculate the dimensions of the null space and the left null space, as long as we know what that rank is. He does a good job working through some examples. You definitely should take a look at these, make sure that you're understanding. And then finally, he goes through his chapter summary. As always, the chapter summary is a valuable thing to review. Specifically, he's emphasizing the RREF. And we've talked about that. We're going to actually talk about it more in the next lesson. But you can see that a lot of what we've talked about in chapter 3 leverages RREF. That is something that is providing a tremendous amount of power for us. Let's just take a quick review. RREF is giving us a way to find the solution to AX equals B when we have a consistent system. It will also tell us if we have an inconsistent system. Unlike MATLAB, it won't just spit out that, hey, the matrix is singular, I can't solve it. RREF will tell us exactly how many free variables there are and what the structure of the solution looks like. It gives us information about AX equals 0, obviously, and really RREF of A is what is giving us the solution for AX equals 0. So that's giving us how to find the null space. That's giving us one of the fundamental subspaces. We know from the RREF of A that the pivot columns are going to give us, when we point those pivot columns back to the original A matrix, that's going to give us the column space of A. We know that the rows that are result from the RREF, the rows from this matrix here, that's giving us a basis for the row space. So just taking the RREF of A is giving us the information about the null space, the column space, and the row space. And really all that we have left to discuss, which will be the topic for next time, is the null space of A transpose, that left null space. So that's it. Let's take a look at the questions. Lot to read this time around. I understand that. But make sure that you're doing the reading. Make sure that you're keeping up. At this point, we've gone through the first 3 chapters. We've used the same terminology over and over and over again. So your comfort level should be higher with that terminology, and you should be more effective at reading as long as you've been keeping up with it as we've been proceeding. The questions for participation are provided right here. We're going to take a look at, of course, the 4 fundamental subspaces. This is a question about the basis, but it's a very simple problem. So you're definitely going to want to RREF this and then just work through, using the information that we've talked about, what the basis vectors are going to be for these different subspaces. And then we're going to talk here about the dimensionality of the fundamental subspaces. That's it, and we look forward to seeing you in class. Thanks.